my brain's exploding. Whoa! Hello, Marauders. We're doing the last section of trigonometry. We're going to do something called work from physics, and also something kind of funny called the dot product. So let's learn this last section. Not too many problems. They just take a little bit of work, and then tomorrow we'll have review, and then we'll be ready for a Thursday/Friday test on trig. All right, here we go. All right, section 6.7, the dot product, kind of funny. And check this guy out. Talk about hard work. I can see the weightlifter's muscles quivering from the exertion of holding the barbell in a stationary position. That means stationary, not moving. Quivering is wiggling, like my fingers wiggling, that's quivering. Still, I'm not sure if he's doing as much work as I, sitting at my desk with my brain quivering from studying trigonometric functions and their applications. Would it surprise you to know that neither you nor the weightlifter are doing any work at all? The definition of work in physics and mathematics is not the same as what we mean by work in everyday use. To understand what is involved in real work, we turn to a new vector operation called the dot product. Okay, so before we learn about how to calculate work, which is a pretty simple equation, we're going to do this funny thing called the dot product, which is basically you've got a couple vectors, like V and W, and dot, it's multiply, V times W, to multiply them together. And it's kind of funny, how do you multiply two vectors together? You just multiply the A component, or the I component, and you multiply the B's, then you add the two answers, and you get a number. So it's actually pretty easy to do. Cool, I like easy stuff to do. So let's look at this example here. Here's a couple vectors. And we have the horizontal and vertical, and they say do V times W. So this is called dot product. I didn't make up the name, that's kind of a funny name. So it says you're going to take the A's times those and add the B's. What are the A's and the B's? The first piece are the A's, the second piece are the B's. See how they got A and B? So we're going to take 5 and -3, we'll times those together, that's -15. Then you take the second one, -2 and 4, times those together, -8, add it up, and you get -23. It doesn't really mean a lot to us, does it? So what does that mean? It's just something we're going to use in a little bit. So they've got the work there. And once again, they did V times W. You could do W times V. You could do V times V. That's the dot product. Pretty easy. Okay, here's an alternative form of the dot product. Instead of doing it the way we did, which was so easy, you could do the magnitude, remember it's a little Pythagorean theorem, times the other little magnitude times a cosine. Oh, why would I want to do that? I don't know. I'll do it the way we just did it. But here's the next thing. Let's find the angle between two vectors. Okay, so like here's a couple vectors. One thing's going this way, one's going that way. Sometimes we would like to know the angle between them. And to find the angle that these two forces are going, or distances or directions, we're going to use kind of that dot product thing. We got this little rule, which looks a little funny. Now, how did they come up with that? Okay, they took this alternative form of the dot product and said, maybe we want to know the angle. Let's solve for cosine. So let's divide these things. The magnitude of V, the magnitude of W, and put them under the other side. V, double bars, W. So the cosine is this right here. So you just move this underneath. And that's what you see right down here. So if we want to find the angle, we're going to set this up, figure out these numbers, and then we're going to do like second cosine to find the angle. But it's easier to do once you see it. Okay, so here's the example problem. It's a good example. Here's a picture of two vectors. One's going this way, one's going that way. Here's the -I plus 4j. Remember, this is like the x. Back 1, up 4. This is just move -1 and 4, kind of like x and y. Back 1, up 4. There it is, -1, 4. Here's another one. This one goes to 3, -2. It's over 3, down 2. Over 3, down -2. what is this angle in between? Here's the rule we're going to use. Okay, so I wrote the formula. I took the formula. Here's the two vectors, v and w, and we're going to put them in this rule. Okay, so first thing, v times w, that's the dot product, what we just did. And what was the dot product? Remember, you could flip back if you forgot the dot product. This little guy times the a's times the b's, add them up. A little funny. Okay, so let's do this part. Try to move this up a little bit. So here we go. We're going to go, here's the a's. 3 times -1 is -3 plus -2 times 4. So these are the a's, these are the b's, times these, -8. Add that up. -11. You've got the top. See how easy this is? Now the bottom. Remember this? That's from yesterday. That's the magnitude. Remember yesterday we saw this? The magnitude. And what do? That's how far it is. How long is a vector? You did the Pythagorean theorem. You're trying to figure out the length of the vector. So when you're doing the magnitude, you're kind of just looking at how long is this vector? Magnitude. How long is this vector? So we're going to do a little Pythagorean theorem. So let's do v. Let's do v's magnitude and his magnitude. There's a little double bars for the magnitude. It's really just the Pythagorean theorem. And that is, let's see, you go 3 squared plus 2 squared. I'm not worried about the negative because the negative would get squared out of there. So 9 plus 4, 13. And then, of course, you got to take the square root. So this piece underneath, this is square root of 13. And see, there's no add here or anything. It's just multiply. Then now do the other one, -1. So this is w. So -1 squared. I can just write 1 because it's going to get squared. Plus 4 squared. 1 plus 16, 17. And take his square root. So put that right there. And you're almost done. So it's just his little Pythagorean theorem. His little Pythagorean theorem. Those are magnitudes. Okay. It's just magnitude is just the length. Okay, then what does this multiply? Well, they're both inside a radical, so let's go 13 times 17. I'm going to peek here. What is 13 times 17? 221. And this funny thing, I could get my calculator and go, what the heck is that? Wait, did we answer the angle? What are we trying to find? The angle between the two vectors. Now remember, there's this other part here. Don't forget the entire question. You can't stop there. It says the cosine of the angle is this. So let's bring it up here. The cosine of the angle is -11 over radical 221. Now, could I just look that up on my trig sheet? It's just like, oh, what angle has that? Oh, that's not one of the ones on here. So remember how we get out of this situation? What angle gives me that? Well, oh yeah, we do the second cosine. So, or some people write this. Like that, put the little -1. So this is where you're going to go to your calculator and go shift or second cosine. There you go. So you got the little inverse. Put this guy in, little parentheses. We've got -11 divided by radical 221. And whoops, I got to get moved to the side a little, close it up. So what angle gives me that? So that's why I use the second. And it says it is a 137.7 degree angle. So theta is 137.7 degrees. That is the angle between the two vectors. Let's check it out. Yeah, that looks bigger than 90. In fact, it's almost a straight line, isn't it? Not quite. It's 137.7 degrees. Pretty cool. So now you know how to find the angle between two vectors. I'm going to skip this part. You can read it on your own. I bet you know what parallel vectors are, vectors that go the same way. Just when you do the math, this is just if you're doing the math and you get down here, what angle is 1? And you go, okay, second cosine, your calculator is going to pop up with, well, 0 degrees. And you go, 0 degrees? Oh yeah, in fact, that's actually on here, 0 degrees. And it's because, oh, they're actually two vectors going the exact same way. And it's possible if you were doing your work and if you got cosine of theta equals -1, and you're like, okay, when you go second cosine, your calculator is going to say 180. Well, that's still parallel, isn't it? And if your calculator, if you're doing the problem and you got the cosine of theta is 0, when you look that guy up, what is 0? Or you can just use your calculator. Remember, you could just go second cosine of 0. It says 90 degrees. Oh, 90 degrees. Perpendicular. They're perpendicular vectors. But instead of using the word perpendicular, they use the word orthogonal. That word means perpendicular. So it's a funny word. Orthogonal means perpendicular. Another word that means perpendicular is normal. Yeah, that's weird. If someone says, here's a line, make a normal to it. Normally we might have a curve, like a circle, and here's a tangent line. You know about the tangent line? Well, if you took another line and said, now I want you to go straight off of it, that's called a normal. That's a normal. I should put it in orange. That's a normal. Orthogonal. So those are all perpendicular. Okay, skip anything about projections. This just makes it kind of complicated. We don't need to do that. Skip all the projections, and we're going to get to work. And this is quite simple. Okay, so work, it says the bad news, your car just died. The good news, it died on a level road, just 200 feet from a gas station, exerting a constant force of 90 pounds, and not necessarily whistling as you work, you managed to push the car. How much work did you do? Well, here's the formula for work. Work is the magnitude of the force. How much force did you push? 90 pounds. Notice how you're getting really low, trying to make this perfectly horizontal, and the distance you traveled. So the formula is really simple. Okay, so here's the formula. Work is force times distance. We don't have to worry about the angle stuff that we just did or dot product. That gets a little more into physics, gets a little more complicated. But here's your formula. The amount of work you do is the force. You're pushed with 90 pounds of force, and you just multiply it by the distance, 200 feet. 90 times 2, you could use a calculator. 9 times 2 is 18 with 1, 2, 3 zeros. 18,000. And we say, what's the unit? We say foot-pounds. Sounds kind of funny. I'll even write it out. Foot-pounds. You did 18,000 foot-pounds of work. That's why the weightlifter was not doing any work, because he's not moving the object. He's pushing, but it's not going anywhere. So since he moved it no distance, apparently he didn't do any work. Kind of a funny definition. Okay, so if you move a 10-pound weight 3 feet, then your work is the force times the distance. Your work is the force. You move 10 pounds, it's the same idea, and you moved it 3 feet. So we did 30 foot-pounds of work. If you did in metric, sometimes you use Newton meters, but let's just use foot-pounds. Now here's a little catch. Let's get some trigging here. This lady is pulling this wagon, but look at the angle. She's not so efficient. She's pulling, but a lot of her work, a lot of her force, I should say, she's applying is not really moving the wagon forward. It's lifting it upward. She's wasting energy. How much work is she doing? Okay, so let's say you're pulling a child and you're pulling with 50 pounds of force. And let's say you move the wagon. How about let's just go 100 feet? Well, here's the thing. You can't just say the work is the force times the distance, because guess what? Your 50 pounds of force is at this 45-degree angle. So you got to figure out what is the x component. See, this is 45 pounds this way. Part of that, you're fighting gravity. Maybe you're trying to lift the wheels over some rocks. You know, if you wanted to pull something really hard, did you ever get down really low? You kind of like, you squat down really low and you pull the rope. I'm trying to draw something like that. You're like, pull like a tug of war. And you get a tug of war, you know, say you get down really low and you try to heave. You're trying to get the rope as level as possible because you don't want to be pulling upward. You know, when you're pulling something, you don't hold the rope way up here and try to pull. Don't you get it down low and try to get it as direct? Well, see, this is not efficient. So what is the x component? How much of this 50 pounds is actually going in this direction? Well, x is the cosine, right? X is this over the hypotenuse. To make it really easy, all you have to do is when you multiply these is just times by the cosine of the angle. That fixes the formula. It's a little hard to catch in the book the way they wrote it. It's not really clear. It's hidden down here. This is the force, this is the distance, and this is the angle. So the formula looks a little funny in the book. So we'll put the force, 50 pounds. We'll put the distance, 100 feet. But because you're not so efficient, we'll do the cosine of 45 degrees. Now, some of you actually have that memorized. You could put radical 2 over 2, or you could say cosine of 45, radical 2 over 2, or 0.707. But while you have that in a number, why don't you multiply now? Just go, okay, we're going to times those numbers by 50 and 100, times 50, times 100. So instead of 5,000, you actually did 3,535, or she did 3,535. I'm just going to round it off. Foot-pounds of work. Okay, that's how it works. So same when you're pushing a lawnmower. Here's a lawnmower. You ever notice that the handle's up like that, and here you are pushing the handle? It's not so efficient. If you hit, like, there's a rock here and you get stuck, well, you're pushing like this, you're kind of wasting a lot of energy pushing the lawnmower into the ground and forcing it into the rock. That's why you kind of get down lower and push from down in here to try to get it over. Or maybe you should stand over here and pull, because that way you could kind of lift the lawnmower up. That's why if you're backing up, you could get over a rock easier. Let's look at one of the questions. So here's a guy. How much work is he doing? Something's wrong with his sled. Dog's pretty smart. He's got the owner pulling him. So he's pulling with 30 pounds of force, but at a 35-degree angle, and he's going to pull 200 feet. How much work does he do? Go ahead and figure it out. Pause the video. Okay, got your answer? Here's my work. Let's see. Work, force, distance, cosine of the angle. That's the formula you need. Sorry, it's a little messy there. I'll make it a little nicer. Force, 30. Distance, it's over here, 200. Angle, 35. Put it on the calculator. There it is. 30 pounds, 200 feet, cosine of 35 degrees. Make sure you're in degrees. And you did 4,914 foot-pounds of work. 4,914 foot-pounds. Okay, so that's it. So let's do the homework. Okay, so here's the homework. I guess all work is homework now, because that's where we're at. So here it is, 6, 7, 1 to 29, every other odd. And these are the work problems. Don't think, oh, wow, boy, that sounds hard. So as you look through these, some dot products, remember, dot product, you look up the rule. Here's a little combination. It says U, V, and W. Let me show you this for a moment. So you're going, what? Hey, what's this? Well, let's be smart. Let's be honor style. U, V, and W right here. It says here's U, here's V, and W. So think about order of operations. Add V and W, add them up. After you add them up, write that vector, then do the dot product with U. In other words, take V and W, I added them up. Let's see, 3 and 1, 4 plus 5. So 4 and plus 5, 4 and 5 is 8. Now dot product of U. U is 2 and negative 1. 2 and negative 1 is U. Here's my new V and W. Now remember, cover those up. Multiply the A's or the I's, if you want to call it, 8. Multiply the B's or the J's. Negative times positive. Negative 5. 8, negative 5, 3. So don't get scared. Throw a few other fancy ones at you. Multiply it by 4 times v. Just look at the examples as you go. Got some ones where you do the dot product. Okay. And sometimes they say, is it orthogonal? Remember, if you get 0, the angle is, I forget where we are. Okay. Yeah. If you get 0, that means what angle has a cosine of 0? It's kind of like, I don't have the cosine written there. You're like, what angle had a 0? 90 degrees. Oh, they're orthogonal. They're a right angle. Okay. And not orthogonal. And then here's your word problems. They're not that hard. Easy to do. All right. Have fun.